Hi everyone, welcome to this new episode of FEA Insight. Today I want to talk to you about the library of elements in FEA for solid mechanics modeling. Well, before learning the meshing rules, it is very important to understand the capabilities and the limitations of the elements that make up the library of elements associated with your FEA software. Today I'm not going to describe all the elements of library of all FEA packages, but I'm going to present the general concepts that are common to all the libraries and that you must know in order to make sure that you are going to do the right choice of element corresponding to the problem that you have to solve. Note that since this presentation is not scheduled for a lot of time, I'm not cover all the details, okay? It will give you an overview of what is a library of element. So it will permit you to go further in your FEA learning process. Let's start with the agenda. I'm going to start with the type of elements used in FEA for solid mechanics. And we're going to cover the degrees of freedom concept, the basic building blocks concept also, and a definition of what are 1D, 2D, and 3D elements. And finally, the spatial elements. Also, we're going to talk about geometry, size, and shape of elements. And I'm going to share with you the rules and the element selection criteria. Finally, I'm going to conclude this video by presenting you how to choose the right elements and the practical elements of the element selections. Let's start with the concept of degrees of freedom. And it is a very important introduction about the library of elements because it's a basic concept which will guide you through your process of selecting the right element. In FEA, the degree of freedom, or DOF, are the fundamental variables of the problems. Okay? In solid mechanics and structural analysis, the degrees of freedom are the translations and the rotations at the nodes of the discretization of the mesh. And not all types of degrees of freedom are necessarily transmitted by all types of elements. And we're going to see that in detail in the next slide. The degree of freedom is fundamental to the understanding of how loads can be applied, how boundary conditions restrain the model, and how the different types of elements can be connected together. So a translational degree of freedom stipulates that a force can be transmitted through a node, while a rotational degree of freedom stipulate that a moment can be transmitted through a node. Now I'm going to present you the three types of basic topologies of elements that are available in all the library of elements of any FEA software. So we have the 1D, the 2D, and the 3D elements. For the 1D elements, the length of the components is much greater than the dimensions perpendicular to the main axis. Typically, for those 1D elements, we have the truss element with 2 nodes and the beam elements, again with 2 nodes. For the truss element, they are long, slender element with 2 nodes that can be oriented in any direction in the 3D space, and they transmit axial force only. For the beam, they are long, slender element with 2 nodes, which can be oriented in any direction in the 3D space, like the truss element, but they have 6 degrees of freedom at each node, allowing 3 translations and 3 rotations at each node. For the 2D elements, they have 2 dimensions, okay? there are 2 dimensions of the component, and 2 dimensions of the component are very large to the other third. Typically, they are membrane or shell element. They can have 3 nodes or 8 nodes, between 3 to 8 nodes. So the description, the typical description of a membrane, it's a 2D element that can be oriented in any direction in the 3D space. And they transmit only the in-plane loading in at each node. For the shell element, they are 2D elements that can be oriented again in any direction in the 3D space. And they can transmit all translational degrees of freedom and the rotational degrees of freedom, or rotational degrees of freedom. But you have to keep in mind that in some software, the rotational degrees of freedom around the normal direction of the element cannot be transmitted. So it depends on your solver. And after that, you have the 3D category where all the dimensions are comparable. So they can have between 2 and 20 nodes. Typically, they are 3D solid elements having various forms, and they transmit only the translational degrees of freedom. So let's start with the 1D element. 1D element are long and slender parts, are used to model long and slender parts. They have 2 nodes that can be oriented in any direction in 3D space, and the length of one element, I should say the length of the element, is much greater than the dimensions perpendicular to the main axis. They can be 1D truss and 1D beam. The truss element is defined by a constant cross section with a torsional constant. Note that this is possible to not define the torsional constant, okay, in the definition of the truss element. And then the element will have only 1 degree of freedom per node, the actual capability. If you specify the torsional content, the element will have an additional rotational degree of freedom around the axis. And the 1D beam element, on the other hand, offers resistance to force, 1 axial and 2 shear, and moment, 2 bending and 1 torsion. So it means 6 degrees of freedom. 6 degrees of freedom. So you see the 1D element is more complex, more versatile than the 1D truss element. The 1D beam elements are usually used when a slender part must be able to transfer forces and moments. And again, you need to define, in terms of properties, you need to define the cross section of the 1D beam element, but also the area moments of inertia for bending in 2 planes, and the torsional stiffness. Here it is an example of usage of 1D truss and 1D beam elements. It is a roof frame, a roof structure model with 1D elements. It is a typical usage. The beam member of the roof elements here are welded end to end. On the other end, the truss members here, you see here inside the roof frame, are pinned end to end. So the beam elements can transmit tension, compression, shear, and bending because they are welded together. On the other end, the truss member, can transmit only tension and compression because they are truss members. They are pinned. I said they are pinned end to end. So they can transmit only tension and compression. So all the 1D elements are connected node to node. But just by changing the choice of element, you change the degrees of freedom, you manage the degrees of freedom that are transmitted between the members. Here you see another example of usage with 1D truss and 1D beam element. It is a bridge, okay? So 1D beam elements are great candidates here because we have long and slender components. Some components need to transmit forces and moments, and some vertical components transmit only axial loads. Another typical usage for 1D truss and beam elements, it is a tower crane. So now let's see the 2D shell elements, how they work and when we can use them. So a reminder here, the 2D elements are 3 or 4 nodes elements that can be oriented in any direction in the 3D space. There are 2 dimensions of the component that are very large to the other third compared to the thickness, I mean. So the 2D elements are triangular and quadrilateral element shape. They are linear elements having 3 or 4 nodes for the linear elements. But we have also the quadratic elements, and they have 6 or 8 nodes. The reason why it is because they have mid-side nodes at the edges. If you want to know more about those quadratic elements, this is covered in the lectures about the library of elements in detail in the practical basic FEA course of FEA Academy. So let's see in detail the definition of the shell elements. The shell element, in reality, it is a combination of a membrane element and a plate element. The membrane element is a 2D planar element that can be oriented in any direction in 3D space, and they have 2 degrees of freedom per node, the 2 in-plane translation. They are used to model fabric-like parts, thin metal shells, or to apply skin elements at the outer surface of 3D elements in order to read superficial stresses. They have very small thickness relative to the other dimension. So only the membrane element can transmit only the in-plane translations. Then we have the plate element. Again, they can be oriented in any direction in 3D space, and they have 3 degrees of freedom per node. The out-of-plane translation and 2 out-of-plane rotations. They are typically used to model structures such as pressure vessels, auto body parts, or even ship hulls. So the thickness is small relative to the other dimensions, over 1/10 to from 1/10 to 1/20. The elements remain planar without warpage, and there is no rotation around the normal of the element. The stress distribution also across the thickness is linear. And finally, the shell, which is a combination of the plate and the membrane, in the sense that the shell have basically all the capabilities of the membrane and the plate. The 2 in-plane translation and the 1 out-of-plane translation, 2 out-of-plane rotations, and not usually, depending on your FEA package, you can have the full capabilities in the sense that all the rotational degrees of freedom are available. But in some solvers, the drilling stiffness is not available. Okay, so you have to manage this effect. So the shell element is like a full capability element. Okay, it's like a thin 3D structure such as panel, sheet metal, or any part having a thickness that is small relative to its global dimensions. The FEA analyst can extract the membrane and the bending effects from the shell elements. So it's a very powerful element. So let's discuss the differences between the triangular and the quadrilateral elements. The triangular and the quadrilateral elements have very different behaviors. And a good understanding of these differences is important for generating an accurate analysis. The triangular element has an excessive stiffness and is usually used in mesh transitions. Transition between two regions of quad elements having different mesh density, for example. So you have to avoid using elements in a region where the membrane stresses are changing rapidly when you have high gradient. The triangular element is a constant strain element. It's very important to keep that in mind. So a large number of elements are needed to obtain acceptable accuracy. The quadrilateral element, on the other hand, should be used instead of the tria when possible, as it behaves very well even when irregularly shaped, and good results are obtained with skew angles up to 45 degrees. In this example, I want to illustrate why quadrilateral elements are preferred over triangular elements in a 2D mesh structure. As I said, the issues with the triangular elements is that they are too stiff for bending problems because they experience constant strain across their entire area. So to obtain an accurate bending response, numerous triangular elements must be used. So quadrilateral elements do not have this overstiffness issue and are the best candidates to capturing the bending stresses in a 2D mesh structure. So here I'm going to illustrate that with a very simple problem, a cantilever beam. So consider the cantilever beam here on the screen made of aluminum having a length of 50 inches with a cross section of 0.1 by 3 inches. The beam is subjected by a force at the end, at the extremity here of 100 pounds at the free end. So with this very basic configuration, it is easy to compute the analytical solution for the maximum displacement at the free end of the beam, as well as the maximum stress at the root of the beam. And it is what you see on the screen. From the geometric and the material properties, we can calculate with those equations the maximum displacement at the free end of the beam and the maximum stress at the root of the beam. The advantage is the fact that we can run the model with different type of elements, different mesh density, and directly compare with the result simulation. And it is what I did and what I present you here. The beam has been meshed with triangular constant strain element and fully integrated quadrilateral plate elements of various mesh densities. The table here summarizes the different mesh configuration. So you see you have first a mesh of quad element with 1.5 inch in size. So it means it's only 2 elements in the height of the beam for a total number of elements of 68. And then you have different mesh size for triangular elements from 3 inches to 0.27 inch. So it means from 2 elements in the height up to 22 elements in the height. So it means from 32 total number of tria, up to 4,070 tria elements, which is a lot. Okay. The right table here shows you the results obtained with each configuration by running a linear static solution and comparing with the analytical solution. You can see that the quadrilateral element is clearly the best choice for accurately capturing the bending effect in a 2D shell mesh structure. In fact, you can see that the 2D quad mesh structure gives an error of 0% for the displacement and 0.3% for the stress, so it's negligible, compared to the analytical result, with only 2 elements through the thickness. On the other hand, when the constant strain triangular element is used, 14 elements across the thickness are needed to produce less than 5% error compared to the analytical solution. So this effect here is illustrated. In a cross-section of a beam subjected to bending, the actual strain and the stress distribution, you know, is not constant. It varies from a maximum at the external fiber to a null value, a 0 value at the neutral axis. Okay, so it means that you have maximum values for the strain at the extreme fiber of the beam, and you have a distribution like that, a linear distribution. So now if you have only 2 triangular elements, constant strain element, it means that you capture only this strain here because on all the elements the strain is constant. So you capture only this strain element, this strain value, sorry, and in this element only this strain value. So you completely miss this variation. So in other words, in order to capture this linear variation with triangular element, and in order to capture each value, you will need to have a lot of element, okay? Because the strain inside the triangular element is constant. On the other hand, with quad element, the strain and the stress vary across the element following a polynomial shape function. It's no more a constant strain element, okay? So the constant strain topology of a triangular element cannot capture this behavior unless many elements are used. It is the key point here in this demonstration. So in other words, yeah, do not use the triangular element to capture a bending effect, or only in transition regions far from the region of interest. Okay. So here it is the illustration of usage of shell elements for a sheet metal part or a car body chassis, or here it is for a boat. Again, it's thin wall structure with width thickness ratio greater than 10 to 20. An aircraft structure, and you see here it's a detail of an aircraft structure without the outer skin, with even the internal elements of the structure are modeled using 2D shell elements. So now let's see the usage of 3D solid elements. They are used to model 3D structures that do not fit the beam or shell description. For example, the castings, the forgings, the blocky structures. They are simpler than 1D and 2D elements, but they tend to generate many more degrees of freedom than a combination of 1D and 2D elements. And they represent a limitation in terms of computing times because they generate a lot of degrees of freedom. Okay? Solid elements have stiffness only in the translational degrees of freedom at each node. So they have 3 degrees of freedom per node. But you are going to create a lot of degrees of freedom when you're going to mesh a structure with 3D elements. Be aware also of potential singularity due to the absence of the rotational degrees of freedom. So it means that you're going to have limitations in applying moment and fixture in rotation with 3D models. You have to keep that in mind. The geometry of the 3 major types of 3D elements are the tet elements, the linear tet element at 4 nodes, and the quadratic tet element at 10 nodes. The eggs or brick elements, which are the 6 faces elements, the linear element at 8 nodes, the quadratic elements at 20 nodes. And finally, the penta or wedge element, the linear element at 6 nodes, and the quadratic elements at 15 nodes. You can create an all tetrahedral mesh, an all hexahedral mesh, or a combination of the two. You can mix them, but you will have to manage the transition between the two. Okay. Also the penta elements are commonly used to model the transition between the tet and the hex mesh. But you don't use them in the regions of interest. Now let's discuss the differences and advantages and disadvantages of the tet and the hex elements. The tet element is frequently used by the automatic mesh generators, which generally manage these elements very well and are capable of meshing all complete solid very easily and very fast. The very last formulation of the tet elements that are available in the modern FEA packages are very good. Okay, we obtained very good correlations against results. So those elements are very good. The tet elements are not recommended in the modeling of the thin walled structures. For thin walled structure, you have to use the shell elements. The tet elements perform very badly. The tet mesh density must be high in region with geometric variation, okay, in the corner, for example, in the radius. On the other hand, the hex elements have superior performance to other 3D elements in most modeling situations, and they are recommended for modeling structure in which bending behavior is dominant. The problem with the hex element, it is the fact that it is difficult to create a mesh with hex element with the modern pre-processing software, and creating a mesh hex requires more planning and preparation of the geometry. So they are create a mesh with hex element. It is time consuming. Here are examples of problems where we use solid elements. Here it's engine crankshaft and pistons, engine blocks, coupling device, propellers. You see, there are no dominant dimensions in those examples. So you have no choice. You need to go in with 3D elements. Here is a braking system. So now let's discuss a little bit about special elements. The first type of special elements is contact elements. The contact element allows you for the simulation of contact iterations between two parts. Also, you have the mass elements. A mass element is a zero-dimensional element, and it is generally used to model the mass of a complex structure when the details are not required. And it is very useful if only the mass of the complex structure must be considered for an inertia problem, for example, or to capture natural frequencies. These elements are generally modeled at the center of gravity of the component that they represent. Another special element, it is the multi-point constraint element and rigid elements. Again, I'm not going to enter into the details of those elements here because they are very, very complex, and they are covered in details into the lecture of the FEA Academy course, which is practical basic finite element analysis. Those elements create relationships between degrees of freedom, rigid elements and interpolation elements. They connect the motion of a node, translations and or rotations, to another node or several nodes. They are typically used to represent a rigid connection not modeled with 1D, 2D, or 3D component, or also to spread a load or a displacement on several nodes. And they create compatibilities between elements, and it's very useful when you use elements having very different degrees of freedom capabilities. So it's very useful to restore the compatibility between elements. They are used also to compute relative displacement or also enforce a separation between nodes. So you can see all the details about those elements into the FEA Academy courses. So now I want to do a summary of the type of elements used in FEA because I present you a lot of capabilities, so I want to do a summary. First, the 1D element usage when one dimension is very large to the other two, the long slender element. The shape, it is a typical line. The type, it's a truss, 1 or 2 degree of freedom, axial and or tension. Typical usage are rods, long and slender parts connected by hinges, or discrete reinforcements. Again, in the 1D dimension, we have the beam with 6 degrees of freedom, 1 axial, 2 transverse shear, 2 bending, 1 torsion. The typical usage, shaft, beam column structure, fasteners, pin joints, vertical post. The last type of 1D element, the spring, with 6 directions defined by the analyst, 3 translation and 3 rotations to model what? Fasteners and interfaces. The 2D elements now used when 2 dimensions are very large to the other third. The typical shape, it is a surface. The first type, it is a membrane with 2 degrees of freedom, the 2 translations. The typical usage, fabric-like parts, thin metal shells, reading elements. The second type of 2D element, it's a plate with 3 degrees of freedom. 1 out of plane translation, 2 out of plane rotations. Typical usage, pressure vessels, auto body parts, ship hulls. And finally, the base 2D element, the shell, with all the capabilities, the membrane, the plate capabilities, to model thin 3D structures such as panel, sheet metal, and any part having a width thickness ratio greater than 10 to 20. Here on the slide is 20, but between from 10 to 20. Okay, the typical thin walled structure. And finally, the 3D dimension used when all dimensions are comparable. The shape is a volume, the type is a solid, the number of degrees of freedom is 3, all the translations. The typical usage is bulky parts like fitting and engine blocks. Let's discuss a little bit about geometry size and shape. To calculate the stiffness matrix, you know that the solver requires that all dimensions are defined. The meshing made up of nodes and elements is used to describe the dominant dimensions with 1D, 2D, or 3D elements selected accordingly. So depending on the element type, 1D, 2D, or 3D, the solver may require additional dimensions. And it is what I want to summarize here. For 1D dimension, the solver considers only one of the 3 dimensions. So the remaining dimensions are defined through property of the element. So the cross-section, if it's only a truss. If it's a beam, the cross-section plus the moment of inertia. Okay? For a 2D element, the solver considers the 2 dimensions in space. So the third dimension, which is the thickness, must be provided on top of the 2D shell element. For the 3D element, the solver already have all the information because you define an element in space with 3 or more nodes. Okay, so no additional geometrical dimension is required. Now let's discuss a little bit about the elements selection. There are different criteria to consider in element selection. First, the element type. Selecting the element type is one of the most basic decisions you will make as an FEA analyst. Okay? Each element available in the library is associated with a family, and each family contains specific building blocks having the 1D, 2D, or 3D topologies. But keep in mind that once a part has been modeled using a specific family, it is difficult to change it. So precise knowledge concerning the various available families is necessary before beginning the modeling work. Depending on the structural behavior of the model parts, the computing time, and required accuracy, you must select the elements from one or several families to model the proper mechanical effects. After that, you have the degrees of freedom. What I want to transfer. When you build an FEM of a structure, you create a mathematical entity representing the structure in matrix form. In structural analysis, the unknowns of the matrix equations are the displacement at the nodes. This displacement at the 6 components for each of the nodes referred to as the degrees of freedom. The number of degrees of freedom assigned to each node depends on the element type. Solid elements, as we saw before, generally have only 3 translational degrees of freedom per node, since the rotations are accomplished thanks to translation of group of nodes relative to other nodes. However, beam and shell elements have 6 degrees of freedom per node. For shell, it can be 5 only. It depends on your solver. The advantages of rotational degrees of freedom is that they allow for the modeling of effects across the element, such as bending to rotation of a node relative to another. So understanding the library of elements depends on knowledge of the degrees of freedom supported by each element, such as number of degrees of freedom at each of the element's nodes and nature of the degrees of freedom, which translation, which rotations, along which axis. This information is usually published in the FEA software documentation. Again, in the practical basic FEA Academy course, there are many examples illustrating those effects. Finally, in the element selection, not finally, but another parameter to consider during the element selection process, it is the capabilities. Each element, you understand that now, has its own behavior or a combination of behavior, tension, compression, bending, shear, membrane, and so on. So the element's behavior dictates the number of degrees of freedom. More possible behaviors require more degrees of freedom. Moreover, not all elements are compatible with all material properties. For example, some elements do not support anisotropic or orthotropic material properties. You have to know that, to keep that in mind when you select your elements. So the material properties must be simulated. The material property that you want to simulate will influence your selection of elements. Finally, not all elements are compatible with nonlinear solutions. So when planning to run a nonlinear solution, certain elements should be prioritized and used first. There is also the accuracy for the selection of the element. For a given topology, certain elements are more accurate than others for capturing a given structural behavior. In a complex model, it is not always possible to use the most precise elements for reasons of computation time. So it is important to know the accuracy of each element you are going to use. Keep in mind that the performance of elements in FEA software are constantly being improved across the different release versions. So you may observe changes in numerical results for a given model in subsequent solver versions. It's very important to keep that in mind. Finally, about the element selection criteria, I want to talk about the cost. In general, the most degrees of freedom an element has, the most expensive it is in running time. Okay? So how to choose the right element? There are 4 fundamental aspects to consider for choosing the right element. The first one is to predict your structure behavior. The critical issue when selecting elements for your FEA is knowing how the structure will behave before you begin your modeling work. You must understand and predict the load path in your structure to be able to select the right elements. Remember that you should not use FEA to predict the behavior of your structure. In fact, you must do the opposite and be able to predict the behavior of your structure to build a reliable and accurate FEA. If you do not have a fairly good idea of how the structure will behave, you may be misled by incorrect results based on incorrect assumptions in your element selection. So you use numerical simulation in order to predict the displacement, for example, or the stresses, the strains, but not how the model will behave. You know in advance how the model will behave. To choose the right element, you need to experiment your library of elements. By that, I mean if you are not familiar with an element, experiment it by doing a very simple test model. This practice will give you a better understanding of an element's capability and the limitations before using them in a large production model, a more complex problem. Before beginning to build your model, make sure you understand all the capabilities and limitations of the elements that you're going to use. The problems can often be solved in many different ways, okay? But making a good choice can reduce effort, computing time, and errors in the results. And you know, it is not very difficult to do, okay? Building very simple problem using all the elements of your library of elements, it's not difficult to perform. But as soon as you have done that, you will have a very good understanding of your library of elements. And when you will face a choice, you will always do the right choice. Finally, make sure you understand the required dimensions for each type of element. And make sure you understand the limitations related to each element, depending on the solution you plan to run. For example, some elements do not perform very well in nonlinear analysis. So let me conclude this presentation by summarizing the rules for selecting the right elements. Prior to defining the mesh density, you must define the element types you will use to solve your problem. At the beginning of the meshing process, it is important to know whether the structure you wish to model should be considered as a shell type or a full 3D type in order to capture the right behavior and local effects, as well as the distribution of the structure internal loads. Moreover, it is important to know the purpose of your model. An engine block, for example, can be modeled with shell and beams if you only want to capture stiffness or dynamic effects. But if you wish to capture stresses in the engine block, a 3D FEA will be required. So let's go through my 10 rules by selecting, for selecting the right elements. First, answer the question, what is the purpose of the FEA? Do you want to capture stiffness, load distribution, or stresses and strains? Which solutions will you run with this model? Static, dynamic, linear, nonlinear, normal mode, buckling, stability? You have to know that before to start, because it will influence the assumptions. Again, it is covered in detail into the practical finite element analysis course from FEA Academy. Another rule is, do you know all the limitations of the library of elements of the solver you wish to run? In other words, do you know your library of elements? And maybe if you change your solver, there are differences between the library of elements. So make sure to read the user manual and to see the limitations and the capability of the elements. When selecting an element, make sure you understand its topology and the associated assumptions and limitations. Use beam elements when shells or solids require excessive effort in meshing. This rule is related to the complexity of the beam elements, which is a very versatile element with 6 degrees of freedom at each node, 3 translation and 3 rotations. Model thin plate structure, okay, with shell elements. The thin wall structure are 10 to 20 times the thickness, or less than 10 to 20 times the edge length. Prefer quad elements over tria elements for the structures meshed as shells, and keep the tria elements away from the zone of interest. My rule of thumb is less than 1% of the total number of tria elements for the complete model. Use tria elements only if you don't have choice, okay? And make sure, as I said before, that make sure that the number of tria elements is negligible compared to the number of quad. Mesh solid parts in 3D solid elements, the eggs or the tet. Opt for the eggs rather than the tet, okay, when you use solid. And use tet elements when the effort required to model with eggs elements is excessive. But in that case, you have to opt for tet 10 and never the tet 4. When you combine different topologies of elements, such as beam, shells, and solids, make sure that you understand all the assumptions in terms of degrees of freedom and manage the transitions, okay? Because it's very important. Keep in mind that all the elements does not have the same degrees of freedom. So maybe you will have to manage the transition between the degrees of freedom. So that's it for this presentation. Again, you can find more details into the book Practical Finite Element Analysis for Mechanical Engineers, available to order in the FEA Academy website. And again, you have the online on-demand courses by FEA Academy, the Practical Basic Finite Element Analysis course with in 20 hours, and the Practical Nonlinear Finite Element Analysis course in 12 hours with many details to guide you, to give you all the assumptions and remove your doubts.